then we can start on today's material. Um, let us see. Okay, so last time we were solving linear equations in one variable. So today we're going to look at linear equations in two variables. It's very similar in concept, but there are some subtle differences that are very important. So when you solve a linear equation in one variable, which is what we've been doing, usually you get a single unique solution. Now this pertains particularly to linear equations, because you might remember vaguely what I said last week is that other kinds of equations might have one or more solutions. But for linear equations, you're only going to get a single unique solution. So if I were to just make something up on the fly, right? Like if I said we had 5 times x minus 10 is equal to 7x. Maybe I want to add 25, right? I completely made up this equation. And hopefully there's a solution when we sort of work through it. So I'm going to just process this really quickly. I'm not going to go through many of the detailed steps here. But what we'll do here is, we'll distribute out, get a 5x minus 50 over here equals 7x plus 25, right? Then since I've simplified the left-hand side, I can go ahead and start rearranging my variables if I wanted to. I could subtract the 7x over here so that these guys cancel out. I should get 5 minus 2. This is sort of that number line thing. So you'll want to be careful, right? If I'm at 5 and I take away 2, I'm taking away 7. Then I'm going 7 to the left-hand side on the number line. So this should be at negative 2x. Again, here it's just like a really neat trick to think about money. 5 minus $7, you're in the whole $2. Minus 50 is equal to 25. I'll go ahead and add the 50 over to the other side so that these quantities cancel out. I'll bring the negative 2x down, and that should equal 75. And then I'll divide by negative 2 on both sides to go ahead and get my x by itself. Since negative 2 divided by itself is 1, I have 1x left over, and this should be negative 75 over 2. It's not a pretty answer, but I can't simplify that fraction any further. So I'm just going to leave it alone. Does anybody have any questions about that processing, right? Went a little bit faster this time. Well, what I'm trying to point out here is that this guy is the unique solution. And when I say unique, I mean that this statement that we started out with, this equation, only has a single number for the solution. If I were to plug this back into the equation, I would get a true statement, something like 0 equals 0. But what I could do with this unique solution is I could graph it. I could graph the solution on the number line. And when you have a single number that you want to graph on the number line, it's usually helpful to, just so that we can place this, figure out, what is the decimal number that this should be close to. So what you might do is just grab your calculator and say, okay, 75 divided by 2 is 37.5, right? So it should be negative 37.5 here. So if I wanted to graph this on the number line, I would say, okay, I need to get to 37. So maybe I'll start from 0 over here, and then I'll count by 5s in the negative direction. So negative 5, negative 10. Maybe I should have counted by 10s, but it's okay. Negative 15, negative 20, negative 25, negative 30, negative 35, and I need to extend this a little bit further. And we'll just say that right about here is our solution. That's x, which is equal to negative 75 over 2. So that unique solution is just plotted as a point, a single point on the number line, because it just represents a single number that you're interested in. Okay, does that make sense? Okay. Well, the nice thing about algebraic expressions, which you see over here on the right-hand side, on the left-hand side, is that they can be, we can talk about multiple expressions at the same time. And when we think about these expressions, as opposed to solving that equation, you could think about the expression as having different values if you give it a different input, right? It has a different output value if you give it an input value. So let me sort of write this down. Let's explore the expression x plus 3, right? Something simple. And what I mean by that is I don't know what this expression is. It's supposed to represent some quantity plus 3, okay? But I can talk about what are the output values if you're given a different value for x. So what are the output values if given different inputs? So in that sense, you can think about this expression as being like a machine, like a jukebox. You're putting quarters in and you're getting a different song out every time. So if given different inputs, the input values here, we usually call the variable x. So what we might do is say, let's make a table. So we might make a table that has an x over here on one side, and then the expression over here, x plus 3, will have some different output value. So I'm going to put in this column the outputs. This is the input side. So what I'm going to ask you guys to do is just shout out some random numbers. I want you to pick some negative, some positive. Let's do about 5 numbers and see how this expression changes. Okay, so let's get like 2 negative numbers in here. Anybody want to venture, just throw out a negative number?
Negative 13.
Let's do negative 13. I heard a different one. Another negative number.
Negative 6.
Negative 6. Cool. I always like to throw 0 as an input. But now can we get 2 positive numbers? And we can keep
2.
them. Yeah, 2 is a good one. Relatively small will make our math a little bit easier. Anybody else want to throw out another positive number?
4.
4. Okay. Nobody wanted to throw out a fraction?
No.
Just kidding. Yeah, we can avoid the fractions, but it works the same way, right? Like what I'm going to do here is I'm going to plug in this value for my x, and I'm going to figure out what the output should be. So you could think of it like equals something. So if I put negative 13 in here, what is negative 13 plus 3?
Negative 10.
Yeah, it's negative 10, right? So this is my output value. So in some sense, like if I plug in negative 13 here into this expression, I get out negative 10. So in some sense, negative 13 and negative 10 are related quantities. Negative 13 and negative 10 are related quantities. Okay, so when I plug -6 into this expression, -6 plus 3, I get what?
-3.
Yeah, I get -3. So there's my output. I'm going to go ahead and circle that or put that in a box. The input that it's related to is -6. And I can just continue going down the inputs, right? I'm going to put a new input in, 0 plus 3. I get +3 there. 2 plus 3, I get 5 there. 4 plus 3, I get, what do I get there? 7. So I have this collection of inputs and the outputs that they're related to, right? What we could do is, instead of, this is what we call a linear equation if we think about it as taking an input and spitting out some output. But usually what mathematicians will do, they'll write this as a linear equation with two variables. And the second variable comes from the output, right? Because it looks like we just randomly chose these input values and then we just sort of threw them into the machine and it spit out some other number, and that was our output. So you can think of this equation as y is equal to x plus 3.
Can you move your paper up?
Yes, ma'am.
Thank you.
Where this expression here determines what the value of y is. What has happened? Oh, I see what happened. Let's see. Document camera. Interesting. Sorry for the technical difficulty. There we go. All right. So this expression, x plus 3 equals y, and you could read it this way or in the opposite direction. So let me put a little note here. It doesn't matter if we write it as x plus 3 equals y or y equals x plus 3, because either way, this statement is saying that the left-hand side is equal to the right-hand side. But when we have these linear equations with two variables, we're going to think about this expression determining the value of y, just like we did here in this table. Okay. So for that reason, we have this vocabulary around linear equations with two variables. So we call, usually, x and y tend to be our favorite variable names. So usually we call the input x or the independent variable. Because we sort of chose them randomly and independent of whatever the value of y was. We then call the output y or the dependent variable. Because again, the expression that contains the value x is what determines the value of y. So y is dependent on x. Okay. And so we could do this again with another another expression. So we might say, okay, so in our last one we said x is equal to, no, we made a table and our y value was equal to x plus 3. we chose -13, -6, 0, 2, and 4. And we put this number into the equation, and it spit out our y value, which was, those are -10, -3, 3, 5, and 7. Okay. So that was our first expression, but we could look at two different expressions, right? Side by side, we might make another table. And just for simplicity's sake, let's say that this expression is y is equal to, okay, so this expression will be 2x plus 3. And again, for simplicity's sake, I'm just going to keep the same values for our inputs. Now, this might be a silly question to ask, but I'm going to ask it anyway. If I plug this number, -13, into this expression, should I get the same value of -10 as the output?
No.
No. And why not? You know, it doesn't even have to be that complicated of an answer, right? But I just want to see where your head's at as we think through this. Why shouldn't I be getting the same answer?
Because you're going to multiply first and then add?
Yeah, because in this expression, I'm going to be multiplying by 2 first and then adding a 3. So it's a different kind of expression. So my output should be different. Right? Like if I put a quarter into a jukebox, I'll get a song out. But if I put a quarter into a vending machine, I'll get a snack out. I won't get the same kind of output because it's a different kind of machine. This is a different expression. So if I plug this in here and I did the algebra really quickly, you know, you could throw it to your calculator and say we're going to have -13 times 2 plus 3. Now, if you put it into the calculator exactly like this, most calculators will conduct the order of operations correctly. It'll do the multiplication first and then the addition. So we should get -23. Well, that should make sense because -13 times 2 should be -26, plus 3 should make us a little bit more positive. So that's why we should get -23 there. Is everybody okay with that, or is that strange? Okay, well, if we throw these other inputs in, -6 times 2, and you know, I'm sort of writing it backwards because multiplication doesn't matter the order. You could do 2 times -6. That's probably a better way to do it because we're putting our input value in for x and then add 3. We'll get -9 here. 2 times 0 plus 3. 2 and 0 should be 0, so this should just be 3. 2 times 2 plus 3 is equal to 7. 4 times 2, I flipped the multiplication, but that's okay, plus 3 is 11. So I get different outputs. Okay, I know that went a little bit fast. Did I lose anybody in just calculating these in the calculator? Everybody clear that, you know, you could just generate these values yourself by plugging these into the algebraic expression over here on the right-hand side. Okay. Well, these are two different expressions, and they have a collection of these related values. And so it seems like if something is going to be a solution for this kind of equation in two variables, you need two numbers in order to determine whether there is a solution, whether these two values will be consistent with the expression here. Similarly, you need two of these values in order to be consistent with this expression over here. What do I mean by consistency? So what I mean is that let's take the values -13 equals x and -10 equals y. And I'm going to plug them into this equation here, y equals x plus 3. And let me see if I need to move my paper up. Definitely do. Okay. So I'm going to plug them into this expression. -10 is equal to, I'm going to put -13 plus 3. Don't mind the parentheses. I'm still just adding. And when I add these and simplify the right-hand side, I get negative 10 is equal to negative 10, a true statement. So you could say that these two numbers, when they're paired together, are consistent with the equation that was given, or you could say that the pair negative 13 comma negative 10, and I'm going to throw that in parentheses, is a solution for the equation y equals x plus 3. Again, because if I plug in this as my x value and this as my y value, then I get a true statement over here. Now I could try this pair to see if it's a solution or consistent with this equation. So let's go ahead and try that out. So we said x is equal to negative 13, and then y is supposed to be equal to 10. And I could ask, is this pair consistent or a solution for, consistent with y equals 2x plus 3? Okay, well, if I go ahead and plug these into the equation, right, as this was supposed to be negative 10, my bad. If I plug negative 10 in for my y, and that's equal to 2 times negative 13 plus 3, and then I go ahead and simplify that, right? So these will make my negative 26 plus 3. And I'm not sure if this is going to be consistent, so I'll just throw a question mark in there. I'll go ahead and simplify this side of the equation. Get negative 23 there and negative 10 here. And then I have this statement, negative 10 is equal to negative 23. Well, that's like obviously false. So the pair negative 13, negative 10 is not a solution for the equation y equals 2x plus 3. Okay. Now I know that was seemingly like maybe it felt like a lot, or maybe it seemed like, okay, this is like painfully simple. I don't know why you went through this process. But I'm giving you guys some time to catch up emotionally and mentally. So do you guys have any questions or comments about what we just went through here? Like if I gave you a pair like this of x and y values and an expression like this, and I asked you, is this pair consistent with the equation? Do you think you'd be able to do it? Okay, let's try this then. Is negative 2, 15 a solution for y equals 3x minus 7? So take a moment to try to figure that one out. And what you'll have to remember here, and I'll touch on this in more detail here, the first value is always the x value, and the second value is always the y value. And when you get an answer, you can just throw it into the chat. Just type in yes or no for whether it's a solution or not. Cool, cool, cool. Okay. Right, not a solution. Not a solution is what I'm getting. So yeah, you would just go ahead and you know, plug these values in. We have 3 times a value minus 7. And my x value is -2. My y value is 15. And then I would go ahead and, run through the arithmetic, the algebra. -6 minus 7 is equal to 15. I don't know if this is true or not, but once I get to the bottom of this, quite literally, I get that this is -13 is equal to 15. And since that's an obviously false statement, that means that this is not a solution. So -2 comma 15 is not a solution for y equals 3x minus 7. Is everybody cool with that?
Is that how you have to write out your answer, or you can just write down a solution?
No, you would, if this was asked on the homework or something like that, you would just say, yes, it is a solution, or no, it's not a solution. So yes or no. I'm just writing it as a statement so that your notes are clear, right? Like if you're copying this down. Okay. So it turns out that when you have these algebraic expressions, these things that we're now going to call a linear equation in 2 variables, you can draw a picture of what this equation looks like, sort of like putting a name to a face. If this equation is the name, then there's a face that goes with it, and graphing is the skill that you're going to need to be able to put that name to a face. Okay, so let me talk just briefly about what we call these things. I'm going to give you a little bit of vocabulary. All right. Related quantities are given by this term that we call ordered. If only I could spell, that's an E. Ordered pairs. Sorry about my spelling. These are written in parentheses. The first value is the input or x value. The second value is the output or y value. And the ordered pair x comma y belongs to an equation and can be graphed. Okay. So let me bring back these 2 tables for those expressions that we were looking at earlier. Okay, I'm going to put them side by side. Has everybody got this down, or do we need a little bit more time to copy this? Okay. So what we could do is say that in table form, I had this x and this y value. And the y value was determined first by x plus 3. And we had -13 -6, 0, 2, and 4 as our input values. And if you plug these into your output expression, right, then you would get -10, -3, 3, 5, and 7. So in some sense, you could write these as ordered pairs as -13, -10, -6, -3. Right? And the x and y values are separated by the comma. And again, they're called ordered pairs because there's a defined order. Mathematicians know that if you write this parentheses and you put the comma in the middle, that the first number is always going to be the input value or the x value. 0 and 3, 2 and 5, and 4 and 7. And if we wanted to graph this expression, we would take those ordered pairs and we would talk about them like their coordinates. In fact, mathematicians do call this the x coordinate, the y coordinate also. And we would put them on a map. Now, because we have two numbers and not a single unique solution, we need two number lines. And what mathematicians will do is they will stack those together. So they do the normal horizontal number line and call that the x-axis. This is where you're going to plot any of the x values. And it's just a normal number line. It starts with 0 in the middle, goes 1, 2, 3, 4, 5, and so on. -1, -2, -3, -4, and so on. But what they do right at the 0 mark is they draw another number line that goes straight vertically down, perpendicular to that first number line. So we have a horizontal number line given by the x-axis, and now we have this vertical number line that we're going to call the y-axis. And naturally, you would think as we go up from this middle point, so let me just put a little highlight here. This middle point at that intersection, we're going to call the origin. That is the central point of our map. And if we were going up in numbers, right, counting up on the y-axis, 1, 2, 3, 4, 5, and so on. It's sort of natural to put the positive numbers in the up direction and put the negative numbers in the down direction. So maybe -1 is here, -2, -3, -4, -5. Right? And so this sort of makes a grid where now we have an x-axis, something to represent our x values, and our y-axis to represent our y values. And we can go to a location, say 2, 5, if we wanted to plot this one. And we might say plot or graph. That means the same thing. By starting at the origin and going over to the 2 on the x-axis, since our x value is 2, and then going up 5. So from the 2, we'll go up 5. And so we should put a little dot right here. And that dot represents the ordered pair 2, 5. Does that make sense? We could do the same thing with -6, -3. Let's go ahead and plot that one. Again, we're always starting at the origin. And then -6 is on the x-axis. So we're going to go to -6 to the left. So we'll go over here. This is -5. I'm just going to extend my number line. You can do that whenever you run out of space. -6 goes over here. So I'm at -6. And then this says -3. So I should be going down 3 units. Okay. So where -6 and -3 intersect, that's where I should be putting my dot. And that is -6, -3. You guys okay with that? And you can draw little dash lines just to guide you to the approximate location. Okay, is any of that crazy? Or do you guys have any questions? Okay, well, let's see about plotting some of these other ones. I don't know if I want to plot this -13, -10, just because I don't have enough space. But 0, 3, you'd start at 0, so that's the x value. +3 would be up 1, 2, 3, so we'd be plotting right there. That's 0, 3. You guys okay with that? 0 in the x direction means you stay right in the middle, and then 3 in the y direction means you go up to +3. And you might notice that, okay, if we plotted 4, 7, we'd go over 4 and then up 7. So you can imagine that 6 would be here and then 7 would be a little bit higher. So if we went over to 4 and then up 7, we would be somewhere like right there. 4, 7. Sorry for squeezing this in. Okay. Okay. Well, then, if you look at these dots that I've put onto the graphing space, right, onto this grid, let me go ahead and highlight them in big and purple. Got one here, got one here, got one here. Doesn't it look like these are in a straight line? Well, if I were to go ahead and take this important tax document as a straight edge and sort of line it up. Now, the only reason why these points aren't lining up is because my drawing is not perfect. But in reality, if you were to graph these perfectly and had a perfect grid system, you should be able to draw a line right through these points, like so. And all of the solutions for the equation fall on that line. Again, don't worry about these guys too much. That's just the imperfection of my art skills. But let's say, for instance, if I were to take x is equal to, I don't know, let's do like -4. What should the y value be? Well, the y value, if I just look at the graph, looks like it's somewhere around here. So maybe we'll be around -2 or maybe around -1. I don't know. Again, it could just be a function of like my bad drawing skills. But we can throw this into the equation, -4 plus 3, and it should spit out -1. You guys okay with that? So again, -4, -1 is like right here-ish. But in reality, it should fall on that line. Okay, so the location of the points for the ordered pairs fall perfectly on the line given by the equation y equals x plus 3. And that's why we've been calling them linear equations, because the picture of these things, the picture of every linear equation, regardless of what the numbers are, is going to be a straight line of some sort. So what I want to do I want to introduce you guys to, just briefly, to a graphing utility that's online, www.desmos.com/ is that the right direction? I think it is. Calculator. Now this is just a graphing calculator or a graphing utility that when we get deeper into graphing, where we have to graph more complicated things, I'll let you guys use them on quizzes and tests. But for now, I just want to use it as a demonstration thing, a demonstration tool. So I'm gonna share my screen. Hopefully this doesn't cause the entire internet to collapse. And so what you guys should be seeing is this graph space. Does everybody see my cursor moving around? Cool. Desmos, if you go to www.desmos.com/calculator, you should see, it should bring you to this page. And over here on the left-hand panel, you can type in whatever equation that you're trying to graph. So we were graphing y is equal to x plus 3. And Desmos is smart. It already knows that you're working with two variables. It's already treating this as the x-axis, the horizontal line. And it's treating our output and plotting every single possible output. So -3, 0. Not sure if that wasn't on our graph here. It wasn't one of our tables, but let's go ahead and see some of the other points. We had 0, 3, and that point is given right here, and it falls perfectly on the line. I said that -13 and -10 were an ordered pair. That's a solution for this equation. So that solution should fall on the line. So if we go over to -13, which is somewhere right here, you could zoom in and then scroll down. We said to -10. I should scroll down and eventually I should get to the line. So I'm going to scroll straight down on -13. And right here, this point right there has too much detail, but -13, -10 is perfectly on the line. And I can zoom out. Boom. -13, 10. Right? -6, -3 was another ordered pair that's consistent with this equation. So I should be able to go to -6. I'll zoom in over here. And -3 should be the y value. So that should be right here. And -6, -3 is on that line. And the one that we just found, -4, is the x value, the input I just gave you. And that spit out a -1. I could go over here to -4. And this point right here should be -4, -1. Okay, does anybody have any questions about this little demonstration, right? This looks like something like the graph that I drew, but this is like a perfect representation of that graph. Every point that falls on this line is a solution that is consistent with the equation. Does anybody have any questions or comments about this demonstration? Okay. Well, graphing is going to come up. We're going to have to graph by hand. So we're going to have to know how to generate these kinds of things. So let's talk about graphing by hand. Okay. Well, when you're graphing by hand, like I said, you want to start with a horizontal line for your x-axis. X-axis starts at 0, but usually I just do tick marks. Maybe I'll throw a 0 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's usually pretty safe. So that's 10 in the positive direction. Each of these tick marks is just a number. And even though, I'm limited by the space on my page, this number line in theory should go all the way to positive infinity. And the same thing going in the negative direction, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You try to keep them evenly spaced if you can, but when you're sort of strapped for page space, you just bunch them up. It just gets harder to read if they're bunched up. So this should be in the negative infinity direction. That's our x-axis. Then I said we're going to do a vertical line that should go straight through that 0 point on the x-axis, and maybe you count 10 tick marks in the positive direction. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Since these look like squares, well, let me say that this is positive infinity in the y direction, and this is down here, negative infinity in the y direction. Okay. Since these are squares, that seem to be cut by this grid space that we've created. We call this grid space the Cartesian coordinate system. But you could think of it as just a graph space. I will call it graph space or the coordinate space. And sometimes it's called the Cartesian coordinate plane. You just have to get used to this ridiculous lexicon that we have in math. Okay, I'll try not to use too many different synonyms. I'm not trying to confuse you. So we have this coordinate plane, this coordinate system, and it looks like it's cut up into 4 sections that are squares, right? It's weird, but we number these little sections. We call them quadrants, and we number them in the counterclockwise direction. So this is quadrant 1. So this is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. The point right in the middle, like I said on the last graph that I just drew, is called the origin. If I were to randomly put a point in quadrant 1, let's say here and here, and let's say that this is 1, 2, 3, 4, 5, 6, 7. 7 in the x direction, and it's like 1, 2 in the y direction. In quadrant 1, my x value is going to be positive and my y value is going to be positive because I went in the positive direction on the x-axis, and then I went up in the positive direction on the y-axis. So these two numbers, even if I'm not given a graph, if I'm given an ordered pair, I should be able to say what quadrant I'm in just based on knowing that these are positive. Over here, you can think of quadrant 2 as you moved to the left, so we're going in the negative direction for our x value. And then we move up into quadrant 2, which is a positive direction in the y value. So if I put a point like, let's say here and here, this point would be given by negative 1, 2, 3, 4. So that's negative 4 in the x direction. And then up 1, 2, 3. I'll put little dash marks to make it a little bit simpler. Positive 3, negative 4, positive 3. So I know that because this is negative and this is positive, I'm in quadrant 2. Okay, well, if I chose this point here, I went negative 1 in the x direction, so that's a negative x. And then my y value is also negative because I went down. So this is negative 1 over here, comma, negative 1, 2, 3, 4. And then if I chose something like this, well, again, you're always starting from the origin. We went over 1, 2, 3, 4. So you start with the x-axis or the x value. That was a positive 4. And then we went down to 1, 2. So that's negative 2 for the y value. So you'll notice that quadrant 4 has a positive x value and a negative y value. Let me go ahead and sort of highlight these. And that's just to help you navigate in the space to sort of figure out where you are. It's fine if you don't memorize that if I have a negative and a positive, I'm in quadrant 2. Because usually what I'm going to do is just give you an ordered pair and then ask you what quadrant is this in. You just draw up a grid, figure out where to plot that point, and then tell what quadrant it is just by counting counterclockwise. 1, 2, 3, 4. Right? All right. Okay, so let's graph another linear equation. Or, let's see. Maybe we need some more practice with getting comfortable with our quadrants. So let's do this. I'm going to draw a grid. This is always sort of time consuming, so just bear with me while I draw grids, as opposed to like just having graph paper on hand. You would think that I would have it on hand, but I'm a glutton for punishment, and I just prefer to draw these out. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I think that should be good. I'm going to label some points, so I'm going to go over here. And I'm going to label this point H. 1, 2, 3, 4, 5. And call this one G. I'm going to call this one right there. I'm going to call that A. And I'm going to call this one right here B. So what I want you to do is take a moment to give the ordered pairs for A, B, G, and H. So just take a second to figure that out. Can everybody see my grid well enough? Do I need to zoom in? Okay. And just for fun, I'm going to ask you to state the quadrant that the point is in. Okay, so has anybody found the ordered pair for A?
6 and 3.
Yeah. So we're going positive 6, 1, 2, 3, 4, 5, 6. I counted correctly, so I'm going to put a 6 down here. Positive 6, so I don't have to write a plus sign. And then up 3 in the y direction, so that's positive 3. Cool. And what quadrant are we in for A?
1.
Yeah, I'm just going to put Q1 for quadrant 1. Okay. Does anybody else want to give me somebody different this time? Give me the location of B, the point B.
0, 3, minus 3.
Yeah, 0, negative 3. Perfect. And what quadrant am I in?
3.
0, negative 3. Well, actually, this one's not. It's really on the
I don't know,
of two quadrants, right?
It's in the middle.
That one's sort of a trick question. We could say that is on the y-axis. So sort of a trick question there. I'm sorry. Yeah, B is neither in quadrant 1, 2, 3, 3 or 4. It is on the y-axis. So usually we'll say that something like that is a special kind of point that you might call a y-intercept, because it's sort of intersecting the y-axis. Okay. What about the coordinates for the point G?
2, negative 5.
2, negative 5. Perfect. Went over 2 and then 1, 2, 3, 4, 5. Yeah, awesome. And what quadrant are we in?
4.
Yeah, we're in Q4 there. Okay. And then finally for the point H.
Negative 6, 5.
Negative 6, positive 5, right? Negative 6, positive 5. And what quadrant are we in?
2.
Yeah. Awesome. Was that crazy? Was that difficult? I'm just trying to get us comfortable with navigating the graphing space. But if anybody has any concerns about it, now is the time to voice them. Awesome. Okay. Sort of a simpler exercise to do, but it's really important to be able to graph these things. So what I want you guys to do is you'll be asked in some situations to graph a linear equation. So I'm going to split you guys up into breakout rooms here, but I want you to think about this problem. Graph the linear equation by completing the table of ordered pairs. Okay. The equation that I'm giving you is y is equal to 2x minus 3. And the ordered pairs that I want you to complete are the following. Negative 5, comma, blank. Negative 2, comma, blank. Blank, comma, 0. And blank, comma, 4. Okay. So these are the values that you need to find. And I'm going to give you very little instruction here. I'm going to break you guys up and see if you can figure out in your groups, how are we supposed to go about completing the ordered pairs? And then once you've completed the ordered pairs, how do we go about graphing those? Okay, so I'm going to. Okay, guys. So like I said, we had this equation and it sounded like everybody was pretty much good on completing the ordered pairs, right? And I didn't give you a whole lot of instruction on that, but I said basically, here's the equation. y equals 2x minus 3. And I said we needed to complete the ordered pairs. And I'm going to go ahead and write this in a different way. You could always do this when given ordered pairs. Here's my x, here's my y. And the first two ordered pairs were -5 and something, and then -2 and something. So basically, I need to find these output values. So when I plug in the x value, I need to get these y values. Okay. But on the other ordered pairs, I was given the y value of 0, and I was given the y value of 4. So when I'm given those two values, then I have to find the x values, because those are the missing values. Okay. So you'll notice that, when you're going through this kind of process, it feels a little bit grueling and arduous in the sense that it seems like just doing repetitive stuff, right? You're just plugging numbers into an equation and then getting some output. And yeah, it feels like that. But once you've done sort of the tedious task of finding the missing value, you have to like take a pause, take a breath, and say, okay, what is the picture? Don't lose the forest for the trees, because it's easy to get lost in the weeds and forget why it is what we're doing, and also what is the importance of this thing. So let's go ahead and just crunch these numbers, right? If I'm given -5 for x, then that means I can plug it into this expression. So I'll have y is equal to 2 times -5 minus 3. You go ahead and simplify the right-hand side of the expression. And really what we're doing now is solving an equation that only has one variable, because there's just numbers over here. Once we simplify that, we're going to have our solution for what y is. So y should be, this is -10 minus 3. So y is equal to -13. Is that what you guys got?
Yes.
Cool. Right, and I don't ask because I'm sort of, playing the role of I'm not sure. I really am not sure because I have not worked this problem out yet. We're going to do the same thing over here. We're going to take our input value of x. So write the expression or the equation y equals 2 times -2. Going to put that input value in, minus 3. And then use our order of operations to solve this equation that only has one variable. So this will be -4 minus 3, which should give us -7. Is that what you guys got?
Yes.
Cool.
Yes.
You guys feeling good about this? Every time you get the same thing that I'm getting?
Yeah.
All right. You should feel that way, and it should feel good, right? Because you don't feel like, oh man, I'm completely lost. I don't even know if what I'm getting is right. Let's go ahead and do this. Now our y value is given, but we don't know the x value. So what we're going to do is plug in the 0 for the y value. So 0 is equal to, and I don't know what x is, so I'm going to leave it alone, -3. Well, this is a simple linear equation with one variable. So I need to isolate the variable. That's going to be the goal. So to isolate the variable, I want to move this numeric term over to the other side by adding 3 to both sides. Right? Slightly different strategy. Over here, we're just we're plugging and chugging. Over here, we actually have to move some stuff around using our rules for algebra, the principle of addition and the principle of multiplication. These guys cancel out. I get 2x is equal to 3, because 0 plus 3 is 3. And then I can isolate the x by dividing by 2. So these cancel out since 2 divided by 2 is 1. So my x value here should be 3 over 2. But for graphing purposes, as some of you guys have noted, it's convenient to put this in decimal form. So 3 over 2, if you throw that into the calculator, 3 over 2 is just 1.5. So this is 1.5 for our x value. Okay, finally, we're going to do that same jazz here. We're going to plug in a 4 for our y, and that's equal to 2x minus 3. Now we're going to solve for x. So I'm going to move my 3 over to the other side. so that these cancel out. Isolate my 2x. Over here, I should have 7. And then I'll divide by 2 to cancel out my my 2's, right? X is equal to 7 over 2, but as a decimal, 7 over 2 is 3.5. So typically I'll want the answer as a fraction, but again, for graphing purposes, it's a lot easier to locate this point if we have it as a decimal. 3.5 comma 4. Okay, you guys all right with that? Well, now we get to graphing. So let me go ahead and draw my coordinate system, or my graphing space, my Cartesian coordinate system. And it looks like I have, when I'm trying to figure out how many tick marks I need, it looks like I only need to go as far as -5 in the x direction. So it might be easy to just count by ones, right? So for the x-axis, I'll start at 0 as always. I'm going to call this 0. And I'll just count by ones. 1, 2, 3, 4, 5, 6. And maybe I'll go 6 in this direction. 1, -2, -3, -4. I'm not going to make it to 6, but all I need is -5. That's fine. And then I'm going to go ahead and do my y-axis here. And since these numbers are a little bit bigger, I'm going all the way down to -13. And I'm going up to +4. Instead of counting by ones and counting down to -13, what I might do is just count by 2's, right? So I'll go up and say that this is 2, 4, 6, 8, and so on. So this will be -2, -4, -6, -8, -10, -12, right? And then I have a little bit of room here to call something a -13, right? So that's one way that you can sort of conserve space. Instead of counting by ones, count by 2's or count by 3's or count by 5's. So hopefully we'll get a straight line out of this. Whenever you take some liberties with the scale, that is, what each tick mark is worth in value, sometimes the graph gets a little squished or distorted, but we should still be getting a straight line once we plot these points. So we have -5 and -13. So we should be going over here to -5 and then down to -13. So try to make that as straight as possible, and we'll call this -13 just a little bit below the -12. I'm going to put my dot right here, and I will call this -5, -13. Okay. Then we have -2, -7, so I'll go -2, -7. I'm going to go down. -7 should be like right here between -6 and -8. So right there at that intersecting point, I should draw a dot. Well, with 2 points, it's always like, yeah, that looks pretty straight to me. But as you start to draw the other ones, yeah, there's a little bit of fudge factor, so I wouldn't worry too much about it. 1.5 would be like over here, and 0 would be right here. So we don't go up or down. We'll just go to 1.5, about right there. Let me label these two. So this was -2, -7. This one was 1.5, comma 0. And then our last one was 3.5 and 4. So 3.5 would be about here, and then we went up to 4, which would be about here. Okay. Nice. And then our straight line, sometimes you get a straight edge out and sometimes you just let go and let God. That's what I'm going to do here. So hopefully it turns out all right. Whee! And there we go. That's a straight enough line. Good enough for government work. And then again, this point right here was at 3.5, comma 4, which was 7 over 2, comma 4. Is this what you guys ended up getting when you graphed the equation? Did anybody get something just really strange? Okay. You guys feel a little bit comfortable with this?
Yes.
Okay. Any questions, comments, or concerns?
Negative.
Okay, awesome. Well, I mentioned this to one of the breakout rooms that there are special points on a linear graph that we have to sort of use vocabulary to understand. And so what I would say is that the points that are right here that are not on the quadrant, but right on the cusp of two quadrants, we don't have it right here, right now. We call this point where the pink line is crossing the y-axis, we call that the y-intercept. And the y-intercept always has an x value of 0. And then we have to find the y value. Okay, so that's just a special landmark. If I asked you to find the y-intercept, then and I didn't tell you what one of the ordered pairs was, what one of the values was, just by me saying y-intercept, find the y-intercept, you would plug 0 into the equation for x and then solve for y. Okay, just by virtue of me saying this term, y-intercept. The point right here where your linear equation crosses the x-axis, similar term, x-intercept. And the x-intercept always has, we don't know what the x value is all the time. Sometimes we have to solve for that. But because we're on the x-axis and we didn't move up or down, the y value is always going to be 0. So when I gave you this problem, one of the points that I gave you to find that had the y value of 0, this guy right here, that guy is the x-intercept of this line. Okay, just some special vocabulary for those special landmarks. Okay, let's take a break. We'll come back in 10 minutes and then we'll finish up our discussion, okay? Recording over again. So we're recording now. Welcome back to the podcast. Yeah, so we need to be able to walk and chew gum, as my dad would always say, which is not always so easy to do. You know, it's he would say it often when he was teaching me how to drive standard. And it is not like walking and chewing gum, especially when your ex-military father is like yelling at you about how simple the process is supposed to be. Fun times, you know, that's going to be between me and my therapist. But what we're dealing with now is walking and chewing gum at the same time, doing two things simultaneously. And you might feel like, okay, we're doing a lot of things simultaneously right now, and that might be true. But what we're going to talk about right now briefly, but in a little bit stranger detail next time, is solving systems of linear equations in two variables. And sometimes you'll hear it say solving these equations simultaneously. So what do I mean by solving a system of equations? Well, a system is just a fancy word of saying I'm trying to solve two or more equations at the same time. And like I said, when we were talking about just a single equation in two variables, that a solution is represented by the x and the y value, right? Is this point, the x and the y, consistent with the equation? Well, now I need to find if a point is consistent with two equations simultaneously. And there's a process of doing this, but I think that it's best if we just jump into an example. So what mathematicians do when they're trying to solve two equations at the same time, they have a couple of different methods. Right now, I'm going to show you the substitution method. And a system of equations is usually written with this curly brace here to connect a number of equations. But we're just going to work with two equations right now. Y equals negative x plus 4 and y equals 2x plus 1. Okay. And the substitution method, if you wanted to solve these equations, you could do this using a graphical method. That is, we could graph both equations and then see what the lines look like. But I sort of want to hold off on that right now. Let's do the complicated stuff first, and then we'll see what the picture looks like after it. To sort of like, I don't know, I sort of like to get crazy before I say, okay, there's a reason for the crazy. All right. So the method of substitution says, if we want to solve these two equations, the first statement is saying y needs to be equal to this expression, right? Y is equal to negative x plus 4. But if I want to solve this other equation, the expression says that y needs to be equal to 2x plus 1. So what we can do is, since this equation says y has to be equal to this, what we can do is just take this equation and plug it into or substitute it into the second equation. Because if y is equal to this, and at the same time y is equal to this expression, then these two expressions need to be equal to each other. So what I'm going to do is say, take this expression, negative x plus 4. That's from the first equation. And I'm going to set that equal to this expression. Right, because this is saying y has to be equal to both. Y is equal to both negative x plus 4 and 2x plus 1. So if y is equal to both of them at the same time, then it must be true that these two are also equal to each other.
Is that always going to be the case?
Yeah, for using the substitution method. That's how you
Okay.
go about it every time.
Okay.
So we set these equal to each other. Now you're looking at this equation, right? So really, I'm going to start here. And I have this equation, and you'll notice that this equation is just one variable, just an x. So what I can do is solve for x, and then we'll sort of do some stuff after that. But we're just solving for x, right? We did that last time. We did it a little bit today. We're just solving for x. So we'll do it the same way we've been doing. Draw my little dashed line. Do my little algebra dance. Gonna move my 2 over here by subtracting 2x. You don't have to start off this way. You could move the numbers first. That's fine. You'll get to the same place. Don't worry too much about that. These cancel. Negative 1 minus 2. So be careful here. Negative 1 minus 2 is going to be negative 3x plus 4 is equal to just 1. Okay. Now we have plus 4. We have to move that over here. So I'm going to subtract 4 on both sides so that these guys cancel. But this will be negative 3 is equal to negative 3x. Okay. And now we can just divide by negative 3 on both sides. because we're trying to get x by itself, right? So I'm going to divide this by -3, divide that by -3. Because again, the idea here is we're trying to get rid of the thing next to the x. This is what cancels out. So x is equal to -3 divided by itself. Any number divided by itself is going to be +1. Let me move that up. So I'm going to box this in. We did that whole process. And now we know what x is supposed to be. Okay. Is everybody with me, or did I lose anybody here? So we set the two expressions equal to each other. We now have an equation in one variable, and we solved for that variable. But this is just the x. We need to know what y is, right? Because our solution is going to be an ordered pair. Well, how do I find y? Well, either one of these equations tells me what y is supposed to be equal to. As long as I have the input value x, I can find the y value. So you can either choose equation 1 or equation 2. It doesn't matter, and I'm going to show you that you'll get the same number if you've done the math correctly. You get the same number, regardless of whether you plug this input value into the first equation or the second one. Okay, so now we need to find y. So let me know that this is like a complicated piece of paper at this point. The first equation says y is equal to -x plus 4. We found x to be 1. So I'm just going to say that y is equal to negative, because there's a negative in front of the x. I'm going to plug in the 1 and then add 4. Well, -1 is going to be -1. So you could think of this as -1 times 1. Either way, this will be -1 plus 4. And so we should get y is equal to 3. And so the solution to our system of equations is the point 1, 3. But it must feel like we just did a bunch of math for no reason, and now we're just calling this our solution, and I'm not sure exactly what this is even supposed to mean, right? Is that how it feels right now? Okay. Yeah, and that's a perfectly natural feeling. And guys, I tell you this, I'm not being emphatic, I'm not being like exaggerative. Math is a lot about how you feel about where it's going. And when students don't understand what's going on, it's harder to get things right. It's harder to feel like you're going in the right direction, but we're trying to build those intuitions so we can sort of have a suspicion that I think because I'm doing everything that I'm supposed to be doing, I think I'm heading in the right direction. And I will tell you that when I work with students on calculus or pre-cal problems, I don't always know where the answer is going, but if I'm doing the right things, if I'm adhering to the rules that we've set forth in this class, usually I can feel my way to the solution and I get something that feels right. But what we'll see here is that this solution means something in the context of these two equations. Okay, so let me write these two equations down again so we can think about what this solution, this point, right? Because we could graph this. In fact, we could graph both of these things, both of these equations. And maybe if I look at the graph of those equations together, that solution will make a little bit of sense. So what we want to do is, you don't have to do this every time, but I think that it's helpful for illustrating what's going on here behind the numbers. We can graph both equations. And we can graph them by hand. But in the, just out of consideration for time, you don't have to graph them by hand. If we were doing it by hand on a single coordinate system, this is what you would do by hand. You would choose input values for x. At least 2. Doesn't matter what those numbers are. Could be negative, could be positive, could be 0, could be a fraction, could be a decimal, does not matter. You get to choose whatever they are. But what you'll do is you'll plug the inputs into each linear equation. So in both of them. And get the output values. So the y values. For each set of ordered pairs, draw a line passing through the points. Since you're dealing with 2 equations, the point of intersection for the 2 lines is the solution for the system. Okay, so I'm going to let that just marinate for a second because I know you guys are copying this down. And I'm going to pull up Desmos really quick. And I'm going to put my equations in, the one we were just working with. I think it was negative x plus something. I'm just going to flip this, plus 4. Okay. Okay. Are you guys ready for the madness? Have you guys written this down or are we still working on it?
I'm still working on it.
Okay. Does anybody have any questions? Or need clarification for this? So again, just to recap, if we were doing this by hand, we have 2 equations in our system of linear equations. So I could choose x values. It doesn't matter what x values I choose. We'll take the first equation, plug those x values in, at least 2 of them, we'll get the output value. I can plot those 2 points and then draw a line between them. I'll do that for the second equation, which will be a different line, right? 2 points, draw a line. And where those 2 lines intersect, that's the solution for the system. So what we've done here without doing it, when we work through this, I gave you a linear equation. There's a graph associated with that. Another linear equation, there's a different graph associated with that. And what we did here was an algebraic way of solving for where those 2 line graphs intersect. They should intersect at this location 1, 3. So let me go ahead and share my screen. Can you guys see the Desmos grid? I've gone ahead over here on the left-hand side and typed in the first equation, right? If you were to get 2 points, and you just need 2 to make any straight line, you would get a line that looks like this. This red line, and it's going down diagonally to the right, right? Okay, let me turn this one off. For the second equation, the line looks like this. It looks like the slope is going up in the positive direction to the right. Okay, so if I plot those two things at the same time, I have two lines and they intersect at this point right here. If I click on this intersection point, it's at 1,3, which is the system solution. Isn't that kind of cool? Right? Like I use this analogy at the beginning of the class, right? There's a name for the faces, or there's a face for the names, right? These equations that just look like a jumbling of numbers and letters, there's a picture associated with it. For these linear equations, it's a picture of a straight line. All the straight lines, they don't look the same. Some of them have a steeper slope. Some of them have a positive slope, that is, they go up and to the right. Some of them have negative slopes that go down and to the right. But when I plot two of these lines together, sometimes, most of the time, they'll intersect at some point. And when we solve for a system of equations, this system, its solution is at that point where the two lines intersect. And you could check this algebraically. So you didn't have to necessarily graph it. You could, and it's helpful to like make sure that you're on the right track. What I would do on a problem like this, which you're not going to see on the homework that's opened up today, you'll see it on homework that we're gonna go into systems of equations more next time, systems of linear equations. But what I would do if you're solving a problem like this is graph it first, then work out the algebra and see if the algebra leads you to a solution that is the same as the intersection point of the two graphs. Right? And that's a good strategy for solving those kinds of things. But algebraically, you could check this solution as well. So let me write down the system of equation again. Y is equal to negative x plus 4. Y is equal to 2x plus 1. And we said that the point 1,3 is a solution to both equations simultaneously. So that means if I plug in, if I take y equals negative x plus 4, and I take y equals 2x plus 1, and I substitute these values in. So in this first equation, I'll go ahead and put y is 3. 3 is equal to negative 1 plus 4. And then I'll put a little question mark because I'm not sure and work my way through it. Well, you'll get that negative 1 plus 4 is positive 3. Positive 3 is equal to 3. So that's a true statement. So that works for the first equation. But if you're solving this simultaneously, it has to work for the second equation as well. So that means I should plug this 3 here is equal to 2 times the x value is 1 plus the 1 that's here in the equation. And this is 2 times 1, which is 2. And 3, sure enough, is equal to 3 again. So that's true. And because they're true at the same time, that means that we did our work correctly, right? The solution of 1,3 is consistent. Or we would say that the system is consistent, that the solution works. Consistent with the system. I'm just going to copy that down. Okay. Okay. I'm not going to do another example of that because we're going to see some more of that at the top of the class next time. So on Wednesday, we'll see some more systems of equations. The homework that you're going to see in MyLabs Plus has opened up already. That is just on working with a single linear equation with two variables, all the stuff that we did, before we went on break. So get in there as soon as you can, work on those homework problems. If you run into any trouble, send me a message, come to Math World, do what you got to do, because we're going to be solving systems of linear equations next time. Not necessarily using this substitution method, but I'm going to show you another method that's stranger. Okay. If you guys have any questions for me, you're more than welcome to hang back, but otherwise I'll see you guys on Wednesday. All right.
See you on Wednesday.
Take it easy.
Thank you.
Thank you.
Thank you.